ammonia, and how we can reclaim our benzoic acid without Rotovap in water, because Rotovap in water is awful and takes forever because of the high boiling point, and because like, have you guys seen a Rotovap? You know a Rotovap? Oh, okay. A Rotovap is basically, it's a really cool thing that's either like super common or like obviously I know what that is, or like no, I've never had a chance to see that. I don't know, why would we have that? But you guys do microscale organic chemistry, so you use such small amounts of solvent you wouldn't need it. It's basically, let's see if I can draw this. That's a bowl with water and it heats up. That's a thermometer. See, you can tell it heats. And then you've got basically a thing that goes here. You fit a, you put it on the outside. You get like a nice little round bottom flask that fits on there, and you put it on with a little clip, I don't know, and there's stuff in here, and this rotates around, and then this end is attached to a vacuum, and then, so you don't actually ruin your vacuum by sucking up all these solvent fumes. You have like a little thing inside a thing with like dry ice and acetone or coolant or something like that condenses all the stuff so it drips down into your little collection flask. And then you have solvent that you got back, and that eventually goes dry. It spins around in there. But like, okay, I guess our Rotovap does, whenever you turn it on, ask if the heat bath is water or oil. So fine, I guess you could use oil if you want, but using oil in a chemistry lab is terrible because it's texture on everything and it's awful and I hate it. So basically, your Rotovap has water in there, and that makes Rotovap in water terrible because boiling off water is awful. And it only goes so warm, and you're also already using water as your, bath to heat it up, so you can only go so hot. So, anyway. So we talked about how we can get this back just by acidifying the solution, so it falls back out of solution, right? That's not gonna work for every carboxylic acid, because some of them are totally just soluble in water, whether they're protonated or not. But for some of these guys that are not soluble in water, you can precipitate them out. Okay. Preparation of carboxylic acids. Carbonation of Grignard reagents. That's really not too bad. I mean, it's very ugly, but like, I think it starts to get the idea across. I think if I showed you guys a picture of a Rotovap, you'd be like, okay, yeah, I can see your drawing is that.
It was pretty good. I've
Thank
used
you.
one before. It looked similar.
Okay, good, yes. My artistic skills know no bounds. Okay, I'm gonna move this so I can talk about it, because this actually blocks your view of the slides, huh? Do you have your stuff going?
Mm-hmm.
All right, here you go, thanks. I will send you access, if you can email me that, it might not work as an attachment. You might have to do like a OneDrive thing, but I'll put it on. No, wait, you guys have access to the OneDrive folder, right? Yeah, you guys have access to my OneDrive folder. So you should be able to upload it, something like that, whatever.
Did you give them edit or just view?
No, everybody has view access. Okay, so
Figure it out.
yeah, email it to me or email me and remind me, hey, I need internet access. All right, carbonation of Grignard reagents. So we can take a Grignard reagent and basically make it into a carboxylic acid. Excuse me. Grignard reagents are nucleophiles, right? and they find an electrophile to attack. So that's what we're gonna see here. And I mostly rescued my shirt from yesterday that I drew all over. I like soaked it in ethanol, because I mean, ethanol cleans these super well. So I just dipped the entire thing in a cup of ethanol in lab, and it mostly came out, but not entirely. I don't know. But like, it's dry erase marker. Ethanol dissolves it entirely. I don't know why it won't fully go away. I don't know. So, preparation of carboxylic acids with Grignard. We've got, what do they have? Fine, I will draw a 5-membered ring. You inconsiderate textbook. Yeah, so this is CO2 gas. And this is our Grignard reagent. We know that our Grignard reagent is our nucleophile right there, because, well, Grignard reagents, they always are. And to find our electrophile, what looks familiar up here? What looks like something that we've seen as electrophiles before?
Carbon.
Yeah, this guy, right? Because it kind of looks like a carbonyl, it's just, you know, 2 of them. So this guy, that's our electrophile. And, well, it's extra electrophilic as compared to like just a carbonyl carbon, because, I mean, it doesn't have 2 carbons and an oxygen. It's got 2 oxygens, and both of those guys have are electron withdrawing, both with the pi bonds, where you can straight up resonate and have the charge separated structure, resonance structures, and their sigma bonds are going to be polar as well, so they're electron drawing on both ends. Although polar sigma bonds mean very little if you have resonance going on. Like, they don't contribute a lot compared to resonance, so we only talk about them if we don't have resonance, or if we have 2 things that both have the same amount of resonance, so we're trying to find what the difference is. Okay. So, we draw our attack. And we get, why am I drawing these so far apart? I'm setting myself up for failure. Okay, that's kind of a 5-membered ring. We have a bond. This guy was our nucleophile. New bond to our electrophile. And what did I forget after my attack arrow? What's wrong with my first step here?
We need another arrow to like oxygen.
What?
We need another arrow to oxygen.
Yes. Yeah, I'm trying to make 5 bonds to carbon, right? Because I'm showing the formation of a bond to carbon, and I didn't actually show that I broke another one. So, there we go. Now, and it doesn't matter if you do the top one or the bottom one. Well, oh, no, we're gonna do the bottom one because, I don't know, I like when carbonyls, they tend to face up, right? That's just, I don't know, carbonyls do that. It doesn't really matter, but I want the carbonyl right side up. So we have this, and then we have this with a negative charge. And then we go, well, what do we do at the end of a Grignard reagent? Water and acid workup, right? So, let's just do H3O plus. This is an obvious acid breakup. So we have and we do a nice little attack. Which direction am I going to start at the oxygen or am I going to start at the hydrogen? Who votes I start my arrow at the hydrogen and point at the oxygen? Who votes I start at the oxygen and point at the hydrogen? All right, so our arrows go the direction the electrons are going, right? So we start them, we find the electrons that we're actually pushing, and we show like, these guys are going to share with this guy, yeah? Cool. So we have that, and this gives us a pentagon. And we did it. So, yeah, that can happen. If I'm being completely honest, I don't think that you have, so I don't think regular Grignard reagents, they're not usually used under like nitrogen when you're trying to react them with other things. So I don't think this is a side reaction that you get just from the carbon dioxide in the air, because it's just not that high of a percent of the carbon dioxide in the air. But also, when we do organic chemistry, there's a lot of, you know what, sure, it's a 1-to-1 mole ratio, but like, take one of your things and put it in excess and just make your reaction go all the way so that you don't have like, you have as few like random half or whatever things, or unreacted of one thing to separate in the column, right? So pick one thing that's gonna be your sacrifice, and I would bet that some of the Grignard reagent that disappears into the ether, that's sacrificed to the gods of organic chemistry, is maybe sacrificed to this. So, yeah. And then also, I added, it wasn't on the slide before, but if you want to prepare a carboxylic acid, well, you can oxidize aldehydes and ketones, right? So if we're looking for ways to do that, we already talked about it, and we're not going to talk about it again, but more than just this one exists. The carboxyl group is very resistant to reduction. So we can do a decent amount of, we can do all sorts of different reduction with aldehydes and ketones. Once you turn something into a carboxylic acid, it wants none of that business. You can put LAH and ether, you have to use LAH and ether and H2O. That will, that's aggressive enough to, sorry, that's the second step, that's the workup, right? Because LAH, we talked about how LAH is aggressive with water, and if there's water in there, then, and LAH even requires nitrogen or argon, right? Okay, I thought we talked about that yesterday, whereas NADH4 does not, but both are, this one's definitely aggressive with water. So, you can use LAH, it is aggressive, and you can reduce your carboxylic acid. You're gonna reduce it to an alcohol. It's always gonna be a primary alcohol because, well, it starts as a carboxylic acid and there's only one bond left that isn't dictated by the fact that it's a carboxylic acid, right? So, always ends up CH2OH. And use LaLH4 and ether, but, you know, again, like most things, we do a workup after that so that the protonated things can get protonated and it all looks normal and happy. acids for this, LALH4, we talked about when we had this on an aldehyde or a ketone, how many moles of aldehyde or ketone could LAH reduce? 4, right? How many moles of carboxylic acid can LAH reduce? Well, let's start with a different question. How many steps of reduction does it take to turn a carboxylic acid into an alcohol? Because when we were talking about reducing a ketone or aldehyde into an alcohol, that's one step, right? We got rid of, we didn't get rid of any oxygens, but we got rid of a pi bond to an oxygen, so made it one step less oxygenated, right? Carboxylic acid has 2 steps. Wait. What do we have here? No, it has 2 steps. I don't know why they have an intermediate here, because it's, oh, okay, because this is before it's protonated. This is just the protonation step. So these 2 steps are the reducing steps. We have 2 reduction steps to get a carboxylic acid to an alcohol, right? So how many moles of carboxylic acid could 1 mole of LAH reduce? I can't hear anyone because it's just so quiet in here, and I'm the only one talking. How many? 2, thanks. I wanted more people to talk, but it's fine. It's all right. Okay. So we can get a lot of selective reduction of other functional groups when there's a carboxylic acid because, like, it doesn't really want to be reduced. So they're not affected by catalytic hydrogenation. You put H2 gas and nickel or platinum or palladium or whatever you want in there and tell it to go, and any carbon-carbon double bonds are gonna go, and any aldehydes or ketones, those are gonna go, right? These guys, nope, they stay put. Yes?
How come there's a 4 and a 3, like molar ratio of those if it only, or 1 mole of LAH, or if it requires 2 moles to reduce? How come there's a 4 and a 3? Wouldn't that be like 1.3?
It's to balance the lithium at the end. That's the.
Oh, yeah,
That's
because the
balance.
lithium complexes to. Okay. Wait, but that still doesn't.
Yeah.
That's a balance. It balances the lithium, but it doesn't.
It doesn't balance the aluminum.
I lied to you. LAH cannot reduce 2 moles of carboxylic acid because maybe it's only NADH4 that's specifically 4 moles, and I don't. Whatever. It's organic chemistry. We don't really care about stoichiometry, right? Like, I'm not gonna make you guys do any sort of stoichiometry, and when you're actually in the lab, yeah, all right, you figure out what your stoichiometry is and how much you need of something, and then you take the things like this anyway, and you put like 1.5 to 2 or more equivalents in because, molar equivalents, so like moles, the same amount of moles times whatever, because it's organic chemistry. We throw a bunch of extra stuff in to make sure that whatever our mostly carbon-having thing, most of that is not left over and turns into the other thing, so we have fewer very, very similar things to separate on a column because columns suck. Difficult columns suck. So, yeah. Thank you. Good call. You can reduce, okay, yeah, so you can reduce aldehydes, ketones, alkenes, and alkynes to alcohols or alkanes in the presence of a carbonyl group. And the carbonyl group will be left completely alone because you're using catalytic hydrogenation, H2 gas, and one of the metals, one of the transition metal catalysts. this is just showing you, okay, that's showing you that. Alternatively, let's see, aldehyde or ketone with NADH4, that is also going to leave this guy alone. And we could guess that, right? Because we already talked about how LAH is, NADH4 and LAH, they are similar, but eventually they're going to be slightly different. Eventually, I swear, I'm pretty sure. But of the two, LAH is the aggressive one, like the really aggressive one, right? And NADH4 is a good reducing agent, but it's not like really aggressive. So if LAH is not going to reduce our carboxylic acid, neither is NADH4, so that's another thing you can use to selectively reduce something. Yeah. And remind me, does NADH4 reduce carbon-carbon double bonds? It does? Okay, cool. LAH and NADH4 both do. Yes? Okay, cool. So, there's literally no difference
I don't think it does.
with our current knowledge, with what we're supposed to know currently in the spans of Organic 2, there's no current difference between using platinum hydrogen and NADH4 LAH in terms of reducing. Yes?
I don't think LiALH does the alkenes.
Oh, does it not?
I think it's just
I'm
rhodium.
pretty sure. I don't think so.
It's just rhodium that does that.
Oh,
Yeah,
okay.
yeah.
Rhodium does that. Yeah, good call. Because we had like all those slides and it was basically just rhodium is gonna do. No, rhodium reduces CC double bonds and does not reduce our carbonyls, right? Okay. Because I know a transition metal catalyst and H2 gas is definitely gonna reduce carbon-carbon double bonds. Let me see what we're on. We got time, I'm gonna look it up, and that way I don't have to tell you, find out and know later, we can just know right now. Okay, so sodium borohydride. Okay, yeah. Sodium borohydride is not going to reduce carbon-carbon double bonds unless you add like ruthenium. And is LAH the same? Yeah, LALH4 cannot reduce alkenes, it seems like. Yeah, okay. So, LAH and NADH4 you can use to leave the carboxylic acid alone and reduce your ketones or aldehydes, and one of the transition metal catalysts and H2 gas you can use to reduce both aldehydes, ketones, and also carbon-carbon double bonds. Yeah, and still leave this alone. There we go. I don't know why they wouldn't just put all of the functional groups that we know about, like that we've studied, on here that can be reduced, and then show us what does. Okay, Fischer esterification. It's 8:41, and we usually have a break at like 8:45, right? Do you guys wanna just do a break now and come back and we'll do this? All right, we've got, okay, have a quick break, have fun,